This is the 18th session. Okay, so I initially thought we'll complete in 15 sessions, but then finally it went till 18 sessions. I extended by a week. So today, this is the last session. So we will start from the point where we left. Okay, so this, remember, this is actually the border of Switzerland and France. So this, whatever you see this here, it's a pipeline. The cross section of that, the close view, you see here. Okay, so it is this tunnel or line. So what they do here, so they try to collide whatever we see as the particles which are inside an atom. So which is what we call as subatomic structure inside the atom. Okay, so why we do that? We do that because if all these guys, they don't behave like how do we normally think. Their real behavior comes out when they have energy, like we told about the classroom yesterday. Without, when the teacher is not there, is when we will see the real Shivananta, the Shivan, the real Ayati, you know, all their antics and tricks and all those things, right? So they, when energy comes, is when they really act. So they need boost and Horlicks. So which is what we do here. So at extremely high speeds, these particles are being allowed to travel and then they may to collide. So we are sort of trying to reproduce the origin of the universe or the kind of energy levels which were there at that time and trying to see what is happening. Because many of these particles which we see above here, they are not stable. They are not stable at normal temperature and they don't stay for much time. Some of them actually stay for microseconds. So to study them, it is extremely difficult. So these are the particle accelerators or what we call as large hadron colliders, where the collision happens. And that is how we try to do experiment on particle physics. So this world of what is happening inside an atom is very different compared to how normal particles behave. So of these, only some of the guys are stable. Like these quarks, when three quarks come together, we get these photons, neutrons, protons, neutrons, and all are actually made with these quarks. Okay, and these people, they have their own characteristics. They have some mass, they have some charge, they have something called a spin, they have something called their area of influence onto how much distance they will act. So some of them are stable. So with that we get proton, electron and all. Many other things are not stable. Okay, so now when we try to learn about particle physics, there are so many complex issues. First and foremost, we saw the light before, like the electromagnetic spectrum. You see, so visible light, you remember what is the wavelength approximate in range? The blue, orange, red and all, in which range? Approximate length, wavelength? Anyone remembers? So it's approximately like 10 raised to minus 6, 10 raised to minus 7 range. You remember Jins was asking you in the Journey of Science course, can you see an atom with naked eye? Can you see an atom?
No.
Can you? Yeah, why you can't see?
Because it's small.
Yeah, this our visible light is bigger than this. So it will cross and go. So to see things of this size, we need light rays. We need rays which are of this size or smaller than this. Then only it will get stuck here. You see? So that is one of the biggest problem in playing with these fellows. And there is one more problem. The second problem is that, you remember we tried to define the relationship between temperature and light, temperature and energy. Remember, Ayati was telling when you increase the temperature, the energy increases. Remember, like the particle's energy increases when you increase the temperature, right? Now, similarly, there is one more important relationship in light. Okay, that is, remember, we talked about that lines in a tall booth. Like if the wavelength is small, like for red light, the wavelength is small compared to blue light. So when the wavelength is small, we told it is like trucks. So in a given time, in 1 second, the number of red waves will be less because it is lengthy. And blue wave is actually shorter. So shorter wavelength is like cycle line or the two-wheeler scooter line. The longer wavelength is like that truck line. So the truck line, you will have less number of trucks because it is longer. And in the scooter line, the same distance, you will have more number of scooters. Do you understand this concept? All of you? This is important. Yes or no?
Yes, sir.
Okay.
Yes, sir.
Others, everyone. Okay. So these are important. This is important concept. So that means what? If the wavelength is small, that means your frequency is less. What is frequency? Frequency is number of waves in 1 second. So if wavelength is small, frequency is less. Number of waves is less. If wavelength is less, they are shorter, means you will have more number of waves. That means frequency is high. Now, there is a relationship between energy and the frequency. So if number of waves are more, means you need more energy to produce it. And you can know it by your normal example. We saw radio waves. They have longer wavelength. They were on the left side of the spectrum, right? Have you seen the equipment which produces radio wave and the equipment which produces X-ray? What is the difference you observe? The equipment which is used to produce radio waves, the equipment which is used to produce X-ray which you see in hospitals and all. What is the difference you observe? First of all, have you seen X-ray machine? Have you seen?
Yes.
Okay. How does it look? Big, small? Radio produces radio wave. That is right. I'm telling you, do you see any difference? What is a simple radio wave producer or radio stuff you are seeing? That's a radio, right? Even the mobile, you have radio in that. Yeah, like
Sir, it
Rishikesh,
is having an antenna.
it is having an antenna. You see the radio, even your mobile, you can tune to radio, right? Even the mobile you can tune to radio stations, and if you have FM radio stations and all, normally these are done by electronic. It's an electronic equipment, right? You will have a very small power. Electronic equipments consume very less power. Have you seen X-ray machine?
It's larger in size.
Yeah, it is larger. It consumes much more power, right? It consumes much more power. So if you want to produce X-rays or gamma rays and all, you need much more power, because the wavelength of that rays are very less. That means the frequency is high. In 1 second, how many waves are there? That is very high, which is what we normally tell as hertz, which you measure in hertz. That is called frequency. So X-ray, gamma ray and all, their frequency is very high, which means you need more power to produce it. You understand? You understand? right?
Yes, sir.
Now the frequency is less, means you need less power. Now here what are we telling? We are telling when the particles become smaller and smaller and smaller, you see 10 raised to minus 13 and all, the ray which we are trying to send should become smaller and smaller in wavelength. Then only, so a ray which is less than 10 raised to minus 13 in wavelength only can detect a proton or neutron. Less than minus 10 raised to minus 16 only can detect an electron or a quark. So which means if their wavelength is so small, then their frequency will be so very high. Much, 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 much higher energy than gamma ray or X-ray. So what does that mean? You need a power plant. You need a power plant of the size of, say, one big town to produce a ray of, say, 10 raised to minus 16 wavelength size. So this is one of the biggest constraint in identifying things which are small. The power requirement is huge. The energy requirement is huge. Do you understand that?
Yes, sir.
Yes, sir.
All of you, do you get that? So this is important, okay? This relationship between wavelength, frequency, energy, and all these all things are the basics of science. Throughout your life, if you are in science, these all things will come to you. Okay, so if these fundamentals, you should have an idea. On top of it, you can build up what is the relationship between this energy and the temperature. So these fundamental things, if you get, these are only few fundamental. Actually, maybe some 15, 20 fundamental ideas are only there. If you get the grasp of it, then this becomes much easier for you. You can understand all concepts, right? Okay. So now this is one of the biggest constraint. So if you have to play with quarks or electrons, you need to send a ray which is very high in frequency, which means very small in wavelength. So the energy of that ray will be very high. Do you observe? Do you anticipate any problem with that? That you send a very high energy beam, just like you think a high energy water jet. You think it is a high energy water jet. So we are trying to measure or trying to know about electron. An electron is rotating an atom. We want to know its position. How do you know? Normally light you can normally see, but you can't see with light. So you create a high energy with high frequency or low wavelength ray and try to hit the electron with that. What will happen? Simple common sense. These are not, see, fundamentals are common sense, okay? The fundamental things are pure logic and common sense. If you have, you can understand all those things, right? If you send a big water jet, very forceful water jet into the small electron, what will happen?
Sir, it will get into pieces.
It will,
It will divide.
yeah, either it may break, okay. If it doesn't break, good point. If it doesn't break, what will happen?
It will go away a little.
Yeah, it will move away. Is that rocket science? So you guys are thinking this is some very complex answer, and that's why you are not answering. If you just put a very high energy beam into this, this will move away. So you want to measure the speed of electron, or the speed of a quark, or the position of the quark. But by the time when you hit, it moves away. What does that mean? You can never accurately measure the position or the speed of smaller particles. You understand? We can never measure that. These are the challenges which we encounter when we get inside the subatomic world. So to understand this, you should know the basic fundamentals that if you want to see something, see only 3 or 4 fundamentals you have to know to get to this point. That to see something, it's all common sense. To see something, you need a ray which is smaller wavelength than that, which is commonsensical, right? Now, if the wavelength is lesser, the frequency is more, the number of waves per second is more. Then, if the frequency number of waves are more per second, you need more energy to produce that. So when you apply a more energy, higher energy ray to detect something, it will move this. So this is a very famous scientific principle that you can never measure. This is one of the biggest finding in the 20th century, that you can never accurately measure the position or the speed of these subatomic particles. Have you heard of any theory with this? Have you heard? Anyone in 10th, 11th, 12th and all? So that is that theory actually changed the world, because till then we were thinking we can know everything about all these things where science advances through research. At this point, we are looking at, staring at that reality that we will never be able to accurately know even where is one electron, what is its position. We can only assume. Okay, so these fundamental blocks all have this property, which is what is called Heisenberg's uncertainty principle. As the name tells, it is a world of uncertainty. Actually, this created huge ripples in the global politics at that time, the global philosophy at that time. Till then, people were thinking science means you can predict everything. And this became actually a big fight between Soviet scientists and the American and European scientists, because on one side they were felt everything can be predictable, and one side now this they are telling it is not possible to predict everything accurately. So Heisenberg actually puts what is the best accuracy you can get. That is the maximum accuracy you can get in measurement of speed or the position of a particle. And this guy, if you are interested, I will give this to you as an assignment. Try to spend some time on this person. He's a very important person. His name was prominent in the nuclear bomb which was produced, which was a very big project called Manhattan Project. There were a lot of discussions and arguments about that. Some scientists refused to be part of it. So you have to understand morality, principles, and science are two different things. Okay? Nuclear fusion, subatomic particle, mass energy equivalence, science. From mass, you can produce energy, is science. Whether you produce a power plant so that you can light up houses, or you produce an atomic bomb to kill people, is not the domain of science. That is the domain of morality or character. That is where faiths and all come into picture. That is where religions and all come into picture. That's what they tell what should be your values in life. It is not a domain of science. So people who struggle, I remember when I took the class on Alan Joshen's school, I think that's how he met up with me first in his that Kottayam school. All the students were asking me, sir, that how do we reconcile between our faith and the science? So these are two different things. What you do with science, with that, whether you create a weapon to kill someone, or you will predict where the cyclone will come so that you evacuate people and save lives, is the domain of faith. Okay? And the same is true vice versa also. The faith also has no role in telling how universe was formed and how earthquakes happen and how tsunamis happen, whether you will pass the examination tomorrow or whether this girl should marry this boy and who will get kids, and and whether if this person should marry on this age or not that age, or this time of the day if you get out from your house then you will pass the exam. This is domain of science. Faith has no role there, and reverse too. Okay, so these two are two different things, right? So this actually, that philosophical clarity had a big catastrophe with this finding out. Okay, so I give this as an assignment to search something more on this person called Heisenberg and this thing called Manhattan Project, the nuclear bomb project, called the scientists who are participating in that, how this energy mass equivalence um, played a role there, and what was Heisenberg's principle there. Okay, so he refused to participate. Right. So now we come to another thought experiment which shook the world. Just now we told that we cannot predict accurately what is the position or speed of a subatomic particle. Along with this comes another bomb, that what is the nature of light is a question which is there from Newton's times. So, Sir Isaac Newton was a firm believer that light is a particle, because light has so many properties which justify that light is a particle. I don't want to get into that, but there are so many properties of light which justifies that it is a particle. But then after that, there was something called double slit experiment. That is maybe another assignment which I can give to you. You can go home and try to do that. It's called double slit SLIT, double DOUBLE, double slit SLIT experiment, which you can do at home. Called double slit experiment, which and some other parameters, some other phenomenon like diffraction and all those things proved that light behaves as waves. So this was a big theory, big debate that light is particle or wave. It displays the character of both. It displays the character of both. And that is a time, a scientist called Planck, Max Planck, he came up with this concept that light can have both property, and the light doesn't come like one particle or one wave. He told light like the data which in the computer networking class Jay was explaining, it comes as packets. It comes as one packet. So you can never have two particles, three particles, four wave, five wave. There is a fixed size of that packet. With fixed size. Only light will come, and sunlight comes, it comes as packet. For you, you feel like it is continuous, but it comes as packet, and that is depending upon something else. That is depending on something else. And Einstein, at that time, he was working on to find out there is a phenomenon called photoelectricity, that when light goes and hits certain kind of material, electrons actually starts getting emitted. So it was a big puzzle for the world. How do we explain this? When light comes and hits something, how can electron go out? Einstein caught hold of this Planck's idea. That Planck got Nobel Prize for that concept. He introduced this concept called photon. Photon is one packet of light. So he told all the rays, electromagnetic radiation comes as packets, and that is based on energy. There is a fixed energy. Okay, so for that energy, to get that much energy, how many waves will be there? That many waves will come in that packet. You see now, just now before we learned that the frequency or how many waves are there in 1 second is depending on energy. So more frequency means more energy. So now here, this is a new concept that you have all electromagnetic radiation comes as packet, and the energy of this minimum size of this packet is fixed, which is what Planck has defined. So he came up with something called Planck Constant. So this, every light ray, every electromagnetic radiation, it comes as one fixed packet which has some energy. So Einstein explained photoelectric effect as this photon with so much energy coming. Who is the other co-host? Ayati, where from the sound is coming? Just mute them. Okay. See where the sound is coming. I think Ben.
Yes, sir.
Just mute. Okay. So where this packet which has certain energy is coming and hitting these atoms in this specific material, and it is causing the electron to emit. It is just like one stuff is coming and hitting something and it is kicking that out. So Einstein also got actually Nobel Prize not for relativity, actually for explaining this photoelectric effect. So this packet is called quanta, Quanta, quanta. That's from where the word called quantum mechanics comes in, right? So we are talking about subatomic world, small particles, and we are trying to understand their behavior one by one. So now we are telling a light can behave both as a particle called quanta and also as waves. Within this packet there can be many waves. That means another uncertainty. And if we want to go and measure that electron or proton to see whether it is particle or wave, you need to send a high energy ray, it will distort it. So you can never measure it accurately and you can never predict it. So this gentleman called Schrödinger, one of the greatest scientists in 20th century, Erwin Schrödinger, he put this thought experiment. He told you put a cat inside a box and this is a poison. If this poison spells out, this cat will die. Box is closed. There is 50% chance for this to fall and this poison to come out. So that poisonous gas will kill the cat. Okay? 50% chance. So after some time, 1 hour say, you are opening the box. What are the chances that cat is dead?
50%.
50%. So Schrödinger was asking, before we open, what is the position of the cat? Is it alive or dead?
Both alive and dead at the same time.
Yeah, exactly. We know there can be only one case. Yeah, what Ayati?
Can you explain this again?
No, see, did you hear the problem first?
Yes, sir.
Yeah, so now you see before, so the problem was you put a cat inside this box and then this is a poisonous gas. There is 50% chance of this falling and this gas leaking. So like Alan told, if you open the box after some time, the cat may either be dead or alive. There are 50% chance. But till we open that, what is the position of the cat? Actually, it can either be dead or alive. Is it not? Only one can be there. But we don't know till we open. Right? So till we open, the position of the cat, though it might either be dead or alive, we can't predict it. So this is the so famous thought experiment called Schrodinger's cat. So the behavior of the particles are like this. You don't know which path these electrons are moving, or this proton is moving, or the subatomic particle is moving. You can only predict that it could be moving like this, it could be moving like this. It could display property of particle, it could display property of wave. So subatomic world is full of unpredictables. So that is what we call as the unpredictable world of quantum mechanics. So one, there is wave and particle duality. Light can either be wave or electromagnetic wave can behave both as particle and wave. Then we are telling these come as quanta packets. So this doesn't come as one wave, two wave, half wave. This comes as quanta. In fact, that explains so many phenomena. And and then we told there is a relationship between energy and frequency. So each quanta has a fixed energy. Each quanta has a fixed energy. Now Planck has defined how much is that. That is what is called Planck constant. Yeah. So Mega, that is the dilemma. How can a cat be both alive and dead? That is the dilemma. That is the dilemma. Okay. So when we tell these electrons are rotating around atom, we can't predict exactly what are the path. We can tell these are the 1,000 possibilities. Out of one, it might be taken, and you can't exactly measure it. Okay. So now everything is based on probability. We are not sure, uncertain. You understand? So these are two different worlds. The one world of galaxies and Earth and F is equal to ma, where we are very sure about something. One quanta is one packet. One quanta is one packet means there we let us assume we defined that the frequency and energy are interdependent. We told that if the frequency of a ray is more, you need more energy to produce that. Which means every wave is, so let us assume you have 1 lakh waves per second. So it has so much energy. So that means every single wave means so much energy. You can relate by telling if you have so many waves in 1 second, it is equivalent to so much energy. So between energy and the frequency, there is a relationship. That is why we told gamma ray, X-ray and all to produce, you need more energy because the frequency is higher. Now, till now, we were thinking the light comes as like one wave from sun or from candle, one wave coming, another wave coming. Or before they were thinking it is coming as particle, one particle, one particle, one particle. Now, the new theory is that the light neither comes as this or the particle or wave. It comes in some energy packets. So you have certain energy, minimum energy. In that energy, how many waves are there? That how many waves are there will change. For the X-ray, for the gamma, for the other one, it will change. Now, in that energy packet, what frequency light can come? So as that packet is how light is coming from sun or from any light source. Yeah. Okay.
So,
Yeah.
how many waves are there in quantum?
You can tell that is depending on, for gamma ray it is different, and for blue ray it is different. That is the characteristic we told that electromagnetic spectrum we call. It is depending on the frequency. For different frequency we call by different name. And for us there is actually there is a calculation for that. For each frequency, what is the energy? So depending on that, for one quanta, how many can be there? There is a very clear calculation.
So,
Yeah.
sir, distance is same with waves may vary.
It is nothing to do with
Depending,
this. It is nothing to do with distance. Is this part? Before we were thinking it is based on distance. Nothing to do with distance. It is all to do with energy. So there is a minimum energy, which is what is called Planck is defined with Planck constant. So that much energy, less than that much energy, light cannot come, cannot even start, or electromagnetic radiation cannot start. And in that energy packet, how many waves are there is depending upon the spectrum where we are. It will be different for radio, different for infrared, different for blue light, different for gamma. Yeah. So it's energy what matters. So we are bringing into this equation that it is energy that is playing this role. Yeah. Okay. So
So,
yeah.
so how did the scientist find out that the light ray is made up of small packets that you
Yeah,
can?
so that is it is like this. The experiments, what Planck did and everything is different. See, root was the last class. You remember I gave you an assignment that what is the color of a star. So that is coming from what is the temperature of that star. So we define that temperature has a bearing on energy. So that energy is defining what color wavelength is more. Okay. So now there were a lot of attempts to explain this spectrum. Okay. So actually Planck came into that as part of explaining this. Okay. They have huge experimental setup. They do not many experiments. But then the clinching stuff was photoelectric effect. So how photoelectric effect can be explained with this and so many other phenomena with light, how it can be explained. Actually, this photon theory, this one explains it perfectly well. And there are so many experiments which further have proved this right. So if you want to really go through that, you can go and check. But this is a done theory. There are no doubts about it. It's a done theory. Yeah. Now we combine both of this. Now we combine the both of this. So what is the predominant understanding about the formation of the universe? As of now, the predominant understanding based on that expanding universe, if you assume this is universe, this is expanding. Now based on this expanding universe, when if this is expanding, that means at one point it should have been extremely small, which is what we call as singularity. There are lots of disputes here. This is not a done theory. This is only a hypothesis. And from here, uh, the you remember now, if the volume if the volume of this whole universe, the entire mass, if it is stacked into such a small part, what would happen? If you just compress the whole earth and make it into a 1 meter diameter ball, what will happen?
Too much pressure.
Yes, Sunda?
The pressure will be so big.
Pressure will be so very high. Atoms will start colliding each other. Particles will start colliding each other. Temperature will go up. Energy will go up. Right? This will be very high temperature. Right? So now these times, this original time, the starting of the universe, that means the energy level was so very high. The energy level was so very high. So, and at that level, we believe that all that four forces which we have learned were one force. So, at high energies, it is expected that all these energies, all these four forces are one force, which is one of the biggest challenge of science today, to reproduce that energy level and to prove that all these forces are part of one force. They have been reasonably successful in combining some part of it, which is called Grand Unified Theory, GUT. This is one of the major area of where experiments are happening, where all forces, it is believed that initially they were together. And then only you had what we call as the fundamental particles like quarks, electrons, and all. And then in that high energy state, these atoms, these quarks and everything will collide each other. Electrons and everything will collide each other. Okay. So if you have, let us assume the quarks come together, combine. and they want to form something called a proton or a neutron, you need some force and energy to do that. So that initially the first force to separate is, it seems, the strong nuclear force. So that can hold the nucleus together. So the first thing which can form is one proton or one neutron. So if you have one proton, what is that element? One proton.
Hydrogen.
That is the nucleus of hydrogen, right? Hydrogen doesn't have a neutron. So if hydrogen, you take one electron out from hydrogen, that is H plus. One proton is H plus. That's why we see maximum hydrogen in the universe, abundance of hydrogen in the universe, more than 77% abundance, because that is the first thing to form, VCR one to form. And then when it expands further, temperature will obviously drop, energy levels drop, and then at that time you don't get electrons to come together to form because they all are separating, all have so much energy. But when it cools down, when it expands, when the universe cools down, that is the time the second force comes into picture, that is electromagnetic force, which is, you see the timelines are mentioned right after some time, and that is the time the electron is coming to fold and atoms started forming. And that is the time then the electron can come and you can form the real hydrogen atom. And when two hydrogens collide, obviously you will get the next element in the periodic table where there are two protons and two electrons, which is what we call as helium. That is the second most abundant stuff. You have most abundance of hydrogen and helium because of this, but then the universe has to expand much more, and then cool down so much so that the further elements, further compounds in the periodic table have to start forming, because till then you have so much of energy, so they don't come and form molecules. So now when this expands, another thing happens. You have like so much of hydrogen, helium all in the atmosphere, and in certain parts of the atmosphere, certain part of the universe, you have more concentration of this dust, hydrogen dust, helium dust, and then they start experiencing what we call as gravity, which is the last force it seems to come out. So then that gravity force against the expansion of universe pulls this mass around it, the hydrogen and helium things around it. You have to understand this, we are talking about like millions of kilometers distance, that much of mass. These are not small things. So it puts this together, and that is how what we call as the stars starting to get formed. And then that is where certain stars will come and form, and then when the stars come and get formed, what will happen? This hydrogen, which are more abundant, which is there, when this gravity attracts this dust and matter to close, these hydrogen atoms will come closer. Hydrogen atoms will come closer, and initially they will repel. Then again, when this gravity attracts and matter comes closer, at one point these hydrogen atoms will start forming helium. Two hydrogen atoms can combine and form helium. And that process produces energy, which is what we call as a nuclear fusion. That process produces some energy, electromagnetic radiation, which we call as light. And that heat produces heat. So you have two things under play. One is the gravity, so that it is forcing the matter to come to the center. But then at that time, this hydrogen atoms collide and form helium, and it produces heat and energy so that it provides an outside pressure. So at one point, these two balance, which is what we call as a star. So star balances at that point. And similarly, the other dust and other particles nearby start getting to form small things, which we call as planets. And on their gravity, when they start moving, and then whatever we explained, the kind of solar system and other things start getting formed. This is our understanding of the universe as on date, as of now. Okay. So now you have to understand one thing.
Sir,
Yeah.
sir, when helium atoms form,
Yeah.
energy increases, right?
No. What happens is when two hydrogen atoms collide and form helium, there is a small mass. The total mass of two hydrogen and the helium what produce, there is a minor difference. So that mass becomes energy. It produces photons. So it creates electromagnetic radiation. So that is what we learned as the energy mass equivalence E is equal to mc square. A small part of mass can produce energy equivalent to mass into square of speed of light, mc square. Yeah. So that produces the flurry of photons, which is what we call as electromagnetic radiation from the sun. A part of that is what we see as visible sunlight. Get it?
Yes, sir.
Okay.
Yes, sir.
So now you see, in this process, when we tell the stars form, then the star will start producing electromagnetic radiation, and because of the mass of the star, the nearby you have something like planets and all those things which form. And in certain planets, when they cool down, these two hydrogen and two helium, they will start hitting together, and the lithium can form, and then beryllium can form, and then after that oxygen can form, and then carbon can form. You see, carbon and all comes much later, much later. And at one point of time, by some force, by some stuff, it creates a one cell called a protein cell, and which starts, because of the mutation, start reproducing, and from there the first life comes, and then they start mutating and start forming different species. So all,
Sir,
yeah.
sir, in the main sequence, star, there is also another part called the small star, in which it comes as a white dwarf. Finally,
We will come to that. We will come to that. That is what this slide is about. Okay. So now all these things are forming from that initial quark or initial force particle. So these quarks form matter, the fermions form matter, and the forces, the four forces which we talked about, they ensure that some action happens between this matter, and with that the entire universe, whatever we see, get formed by that. Now we look into another scenario. So that scenario is what Alan was mentioning now. So the star, what will happen if the hydrogen in the star gets over? Hydrogen atoms collide, form helium. It produces energy. So that energy provides a pressure. So there is one gravitational pull towards the center, but the pressure, because of this nuclear fusion to outside, it balances. The sun is balanced or star is balanced. What happens? This hydrogen is getting over. So this was a puzzle in the 20th century. In fact, there was a lot of research which has happened in that area. There was one Indian scientist called Subramanian Chandrasekhar, who was a Nobel Prize winner, who actually put together one sound theory in that. So it was that if a star hydrogen is getting over, the helium will still continue to collide each other and start producing some kind of a fusion, but it won't be sufficient enough to hold this gravitational attraction towards center. So the star will start collapsing towards center, but some helium based reaction will happen, which is what we call at that moment is what we call as a red star or something. It will show some light, it will throw some light, but that pressure won't be sufficient like the hydrogen based nuclear reaction. So the star will start collapsing. The star will start collapsing. And star will start collapsing. And when it collapses and becomes pretty small, the atoms will come closer to each other. And when the atoms come closer to each other, the protons will get closer to each other. The electrons will get closer to each other. You know, at that time, there is something else happens. So there is a principle that I don't know whether you have learned. Two electrons of the same speed and of the same speed, and there is something called a quantum number, which won't be there in the same position. They will repel. Two protons, they won't be there in the same place. They will always be at a distance in the space. So that is a character. That is a theory called Pauli's exclusion principle. I don't know whether you have learned Pauli's exclusion principle. Actually, it's a very important principle. If that was not there, all electrons and everything would have come together, all protons, everything would have come together, and you would have never heard any matter. Our mobile phone and our laptop, our wood and everything would look similar because everything all electrons. So all electrons end of the day. Everything will come close. So these are possible because the molecular structure of each of these things are different. So the position of the electrons and these orbits and everything are different. That is why it is possible. And that is possible because they can't come closer after some point. So once they come close, then they will start retarding. Okay. So when this star collapses, when these atoms become very closer, then these electrons will start pushing each other. And that will produce some outward pressure. And it will balance the gravitational force of the star to collapse inside. And the star will be stable in that position, which is what we call as a white dwarf, which is what Elon Musk mentioned. There are so many white dwarfs which you can see in this space. It is much smaller, few kilometers in radius, much smaller than sun because the star collapses. And then at one point, these atoms will come closer, the electrons will come closer, they will start repelling. And when the gravitational collapse is too much, then this electron collision will also become too much and they will repel much each other, and that force of repulsion will hold the star, which is what we call as a white dwarf. You can see so many white dwarfs in space actually. But then the problem was not that. Problem was, this is possible. 4 stars, say 1.5 times or less than 2 times of sun. For stars of that size, this happens. What will happen if the stars are bigger than that? If the stars are bigger than that, the gravitational pull towards center is much higher. That this Pauli's exclusion principle based electrons repulsion won't be sufficient to hold that. In fact, that is what shocked the entire scientific community. What will happen further then? Will this collide further? Yes, it will become smaller. It will become much smaller. But there is another possibility, like instead of electrons, the repulsion not able to hold, but then the protons inside the nucleus, they can also become much closer. Neutrons can also become much closer. They can also provide some repulsion, and that may sometimes hold that star, which is maybe stars of some 1 kilometer, 1.5 kilometer radius and all. This is what we call as neutron star, proton star and all. But then if the mass of the star is much bigger, this force, this outward pressure also will not be able to hold this, which means the gravitational pressure of the star will continue to shrink the star, and it will become so small, so much of mass concentrated in such a small place, so that it will start attracting everything close by, including light, which is what we call as a black hole. So now this was actually very difficult to digest. This is very similar to the formation of universe. We are telling the mass can be concentrated into one specific point, and we can't take the photo directly to, because it can even attract sunlight. So that even Einstein refused to believe initially that this can happen. So actually it is actually coming from his general relativity theory only. So this is actually the life and death of some star, but then black hole itself is a very big area. I suggest, if you have interest in time, you can go and search about that. Why it is very important area? Because it can give some clues about formation of universe. It can get to give you some more information about the space, about things which happen inside the space and all. Okay. So now our galaxy, which we talk about, which is what we call as Milky Way. So which is, the size of that is approximately this much light years to travel. So if you're traveling from one side of Milky Way to other side, it could take, if you're traveling at speed of light, more than 1 lakh years. Okay, right. So there are different categories of galaxy. Ours, we call it as a spiral galaxy, and you see this many billion stars like sun are there in our galaxy, only in Milky Way. Sun is one simple humble star. 1 billion is 100 crore. Okay, 100 into 100 crore stars are there in our Milky Way. Okay, so now 100 plus billion planets are there, right? And you see the rotational period there. The galaxy also rotates. We believe that in the center of the galaxy there is a black hole, and that rotational period is like 1 year for the Earth to rotate on its axis is 240 million years to complete. But the speed is so very high, much more than the speed of Earth around the sun, 600 kilometers per second. Which means we all are moving at the speed. Like Earth is rotating on its axis, Earth is rotating around the sun, and we all, the entire solar system, entire galaxy is rotating around its center. Okay? And such a huge mass. If sun is one mass, 5.8 into 10 raised to 11 masses of sun. And about universe, if you talk about the age approximately, but if you start from one side of universe, the other side would be 93 into 100 crore light years. That is the distance. Okay, so if you're intelligent, you may find some discrepancy here, that in 13.8 billion years, how can something become 93 billion light year? Because even if the universe was expanding at the speed of light, the whole length of the universe should have been only 13.8. So if you want, you can go and search about this. That is what is called the expansion phase, inflation phase of the universe. You can go and study if you are interested about that. And there are 2 trillion, trillion is 1,000 billion, 1 lakh crore galaxies are there. 2 trillion plus is the current estimate. Okay, so what is science doing now? Science is trying to think about how the universe got formed, how it got origin, will it collapse ever? And science is talking about something like some terms which are unknown to science. What are the unknown terms? Well, I'll complete this and I will take questions. See, when we know what is the approximate speed of expansion of the universe, and we also know the time a galaxy, most of the galaxies like our galaxy takes to rotate. And we also have with that some calculation about the gravitational attraction of a galaxy and also of the whole universe. So, but now if we add up the entire matter in a galaxy and calculate the gravitational attraction, we still get only some 4 or 5% of the gravitational force which we are observing. Which means the rest, say 95% of gravitational force, where is it coming from? We don't know. For the whole universe also, for the galaxies also. So that means there could be some matter around, but we are not seeing it, which is what we call as dark matter. So it's one of the biggest area where science is trying to spend some time and find out what is this dark matter? Where is it coming from? Where is this much gravitational attraction coming from? Now there is another phenomenon, Alan. Okay. So there is
how do we know the presence of dark matter? Dark matter is there.
Yeah, so how do we know it's from the calculation, because from the calculated gravitational attraction of a galaxy, we have a reasonable idea. Like in the solar system, we have calculated how much is the gravitational force between Sun and Earth. So like that for the galaxy also, from the center of the galaxy, what is the gravitational attraction? We have a calculation. But if you add up the entire matter, entire planets, entire solar system, entire stars of the galaxy, the matter, how much you get, the mass you get for that gravitational attraction which you observe, it is not sufficient. It is only 1/10 or 1/5 of that. That is why we know there is a dark matter, but we don't know what is that. That is why it is called dark. Now, similarly, there is another phenomena, that the way in which universe is expanding, and universe speed of expansion is increasing. So its universe speed of expansion is increasing, and if it is expanding, overcoming the gravitational pull towards center, that means there is something which is causing that expansion, that is against gravity, or what we call as anti-gravity. Gravity is trying to pull the universe towards center, pull the galaxy towards center, pull the solar system towards its center, sun. But then something which is causing this expansion, and that expansion rate is increasing. Again, we don't know that. What is causing that? But there is an energy, as per calculation, as per observation, which is what is called dark energy. And it's another one big area of science. Okay. Now, another region where so much of research is happening is the special theory of relativity, whatever we told, and the quantum mechanics. A decent reconciliation has happened. But general theory of relativity actually doesn't go well with quantum mechanics. Because in quantum mechanics, everything is in terms of quanta. But in general theory of relativity, we are telling the space-time itself is curved. But then can we tell space-time as quanta? Till now, it's not been possible. So there are so many other complicated issues also when we apply quantum mechanics to general theory of relativity. So now that is what, I don't know, I suggest you all to see this movie called Theory of Everything. And that is, I think, Stephen Hawking's life-based stuff. So,
Sir, it's also given in the book of Stephen Hawking.
Yes.
Answers to brief questions.
Exactly. So Stephen Hawking has written a book also called Theory of Everything. So
yeah,
that is
the marriage between quantum physics and general theory of relativity.
Exactly. So, but we have not been successful till now to find out a theory. There have been stalled attempts. One attempt is called string theory to explain quantum mechanics and relativity into one. And another very recent attempt is which is gaining much more currency today, is called loop quantum gravity. So I am putting all these things is not to confuse you. If you want, if you're interested, you can go and try to read and hear lectures and all. You may understand some part of it, but that is fine. GUT, we told that all forces were one in the beginning. How to reproduce that? And black holes, another big area. And then are there more particles? I remember Rishikesh presentation. Is there a fifth force? Are there other more particles? So another area of science today. So with that, I end this course of science. Uh, I, I hope all of you had some takeaway from this. I believe all of you will become citizens who follow scientific temper, who at least follow some rational thoughts, who don't run behind superstitions, but who use science for humane purposes to improve the life standard of the people around you, especially the people who are really disadvantaged and struggling. So with that note, with a big thank you, I stop this course. Thank you very much.